Guy de Lombard, here right here for a physics review for a couple of problems that I promised I would do a video on. So this is based off of the Chapter 5 review, and here's our, so Luzario is piloting an airplane at an altitude of 100 meters and a speed of 190 kilometers per hour, drops a container of swag bags for his fans. Air resistance is negligible. How far in meters does the container travel before it strikes the ground? Okay, well, first thing you want to do is go ahead and make a drawing of the problem. Okay, and we know that we have a plane. Okay, never mind what my drawing looks like, and we know that the plane is about 100 meters, so our D in the Y direction is 100 meters. Remember to make the distinction between your x-axis and your y-axis. Okay, remember with your x-axis it's the horizontal, your y-axis is your vertical. Okay, because Krispy Kreme says so. Now, so this is the height that we have. Now, at the same time though, we also have a dx. So that's our distance in the x direction. Okay. We also know that the plane is traveling horizontally. When we say a speed of 190 kilometers per hour, we're assuming it's traveling horizontally. So that's going to be 190 kilometers per hour. Okay. Now we also know that we have the acceleration due to gravity. That's our 9.8. We may or may not need it. But we need to get all the facts there, and it helps if you go and sketch out the problem. Now, since our character is dropping a package, okay, the package isn't going to go straight down like this. And the reason for that is because the package, along with the plane, is traveling this way. So really what you're seeing is something more like this. So you're seeing an arc. Now, for our sake of argument, it's a straight line, and we will go and work with that, okay? We don't count for air resistance and all that other stuff because that would require another type of thing. Now, the first thing we're going to need to do, we have to make sure that our units are the same. In other words, meters and seconds. Now, we were given a velocity in kilometers per hour. So we're going to need to do a little bridge notation action. So let's go change it. So we're going to have 190 kilometers to 1 hour. Okay? Now the thing you need to understand, when you put something in a bridge notation like this, you can't have two units in the same box. It's 1 unit per box. That's a very important thing. So I got 190 kilometers and I need to change that to meters per second. That's my goal. Okay? So I'm going to go ahead and it doesn't matter if I change the hours to seconds or the kilometers to meters. It doesn't matter. Okay? As long as you know how you're setting it up. Because you want your units to cancel out. Now if I take 190 kilometers and I change it to meters, that's going to be a pretty big number because 1 kilometer is larger than a meter. So we're taking this and we're making meters out of this. That's going to be pretty big. So you know what? It's a pretty good bet. We're going to be putting our 1,000 meters up here to 1 kilometer. Okay? So we've done that. Now we're going to turn around and we've taken care of our kilometers. Let's look at hour. Okay, and for the sake of argument, I'm going to go ahead and say that in 1 hour, I have 60 minutes. Okay? You'd say, but wait, why did you put that up there? This is a bridge notation thing. Remember, we want our units to cancel out. That's important. Okay? All right, and we've got one little more step to do. And that, ladies and gentlemen, is dealing with the 1 minute is 60 seconds. Okay, so that's what we have, ladies and gentlemen. So we're going to go through. Now let's check and make sure because, hey, I could be wrong. Okay. So I'm going to go ahead and I'm going to draw a cross through the kilometers. So kilometers are out. I'm going to draw a circle through the minutes. Okay. And I see one last thing here. I'm going to take the hour, and I'm also going to cross that out here. Now notice I color-coded it and I made the same symbol so you can see that the exact units are canceling out. This is a bridge notation thing, okay? I do have a separate video dealing with bridge notation. Okay, you're going to multiply this all the way across, and you're going to get 190,000 meters over a big whopping 3,600 seconds. Big number, but we gotta reduce this. We somehow need to change this. So when we divide it out, it's going to equal a big whopping 52.78 meters per second. Okay, so that's pretty fast, I gotta admit. So that's how fast our plane is, but that's also how fast our package is going horizontally. Now the next thing we're going to need to find, so what we have, ladies and gentlemen, we have our V in the X direction in the correct format of meters per second. We needed that, okay? But now the next thing that we're going to need to find, we've got to find the time. How much time does it take to fall? Now, you need to understand something. The time that it takes to fall in a straight line is going to be the exact same time that if you're falling in an arc. And that's the important thing that you have to realize. The time for the X version of motion is going to be the exact same time as it is for the Y version. So when we figure it out in the Y version, that also applies to the X version. That's a pretty important concept. So let's go ahead and find T. Now we got to look and see what are the possible formulas that are available. Remember, when you're trying to choose the formula, you want to choose the formula based on the actual information that you have. Okay? You know you need to look for time. You know you have Vx. Okay, that might be useful, possibly, but you have dy. So when you're looking in your formulas, okay, you're going to have dy is equal to 1/2 g multiplied by delta t squared. Now that's the formula that you're going to be able to use for this. Well, you have dy. We know what g is. That's 9.8, because remember, that's a constant. Okay, and then your delta t. Well, wait, I thought we were trying to find t. Right, remember delta t is the change in time, the time at start to the time at the end. Now, in this case here, our time at the start is 0. So we can reasonably assume that our time that we're calculating here is the time at the end, and that's our delta t. You could look at it as our t final. All right, so let's go ahead and let's plug in some numbers. So I know that 100 meters, and that's our dy, we got that from up there, is equal to 0.5 times 9.8 times our delta t squared. Now if you want to substitute x in there, you could. That's up to you. All right. Wait, Canu, where did you get the numbers? All right, let's fit this in. This is our dy. This is what they gave us. Okay? This is our 1/2. This is our acceleration due to gravity. So now you know where those numbers are coming from, and it's a part of that. We can go ahead and multiply this out. And what we're going to end up with, ladies and gentlemen, we are going to have 100 over 4.9 is equal to t squared. Okay? That's what we're going to have. When you solve for t, we're going to do the 100 over 4.9. Wait, what does that mean? Let's go back, and this is where the algebra kicks in. Okay? In order to get t by itself, we have to divide both sides by this. Okay? So if I'm dividing both sides, okay, I'm going to divide both sides Because remember, what you do to one side of the equal sign, you're going to do it to the other, right? That's what you're going to do. This completely cancels out. I'm left with my t squared. My delta t squared is equal to 100 divided by 4.9. So I'm going to go away with 100 divided by 4.9, and that's going to equal our t squared. So our time, ladies and gentlemen, is 4.52 seconds. So that's our time. Yay! We figured it out. We figured out the time. Now what does that do for us? Well, remember, when you do the time going down is the same as the time going across. So when this thing hits here, the time is going to be the same as if the projectile dropped straight down. Remember, we're not taking into account air resistance, wind resistance, we're not taking into account humidity, temperature, time of day, whatever holiday there may possibly be, the phase of the moon, the phase of the tides, okay, the will of some irate god, okay, it doesn't matter. The time is going to be the same, coming down here or going here. All right. God has a sense of humor. What can I say? All right. So there are certain natural laws, and it doesn't want to come down. Come on, come on, come on. Okay. Now that we have that information, we now have, so we have our Vx, that's equal to 52.78 meters per second. Remember, we changed that 190 kilometers per hour into meters per second. So that's our Vx. Okay, now we have a time of 4.52 seconds. Now we get to find our dx. Now the formula for dx is equal to v in the x direction times our time. Wait, isn't that the same as delta t? Yes, it's the same as delta t. That will work, okay? So dx is equal to 52.78 multiplied by 4.52 seconds, okay? So we're going to walk away with 238.56 meters. So that, ladies and gentlemen, is how you solve the problem of Lucerio dropping the package at a height of 100 meters at a speed of 190 kilometers per hour. How far in meters does the container travel before it strikes the ground? Okay, remember, the time going down this way is the same as the time going this way. All right? So with that, guys, you're now seeing it. And let me change the view so you guys can see the whole thing. Okay? There you go. So we changed the speed to meters per second. We had to find the time because we have the dy, we have our g. So we worked all that. We got 4.52 seconds. Then we were able to take that and plug that into here, into our formula, dx equals vx times t, straight on through, and we got 238.56 meters. That's it. Okay, that takes care of one problem. I was asked to do another, so we're going to go and we're going to do another. So here, we've got another one. So Lucerio has a swag bag he no longer wants. He lets the bag roll down a slope and it bounces horizontally off the ledge at the top of the cliff of the Talentless. Its horizontal velocity as it becomes airborne is 10 meters per second. The swag bag strikes the ground 30 meters from the base of the cliff. How high is the cliff of the Talentless, and what is the swag bag's speed just before it hits the ground? Okay. Well, this is one that we're going to have to do a little bit of drawing in order to understand. So we know that Lucerio is, you know, he lets the thing roll on the ground. It comes to a cliff, okay? So he lets this ball, he lets the swag bag go down, hits here, and then takes off at 10 meters per second. That is our v in the x direction. Okay? Now, he also gave us, ladies and gentlemen, He also gave us, the problem also gives us our dx. Now our dx is equal to 30 meters. They gave that to us in the problem. Now remember, how in the, wait, Canu, I'm not following you. There's a lot of words here. I'm getting confused here. How do we handle that? Well, first thing I gotta do is look at my time. Ooh, I am running out of time. So I'm gonna have to stop this one, boys and girls, and I'm gonna have to come back to you in a part 2. Toodles!